Okay, excellent. Thank you. Thank you for the opportunity to speak here. I am going to talk about some very explicit diophantine applications of Heegner points. So my job today is to show you some of the beauty in the examples, to show you a lot of numbers and computations and just nitty-gritty details. And so hopefully you'll get to see some of the beauty of the subject that way too. Okay, so before I say anything more, let me say that everything I'm presenting today is joint work with Samet Dasgupta at Harvard, and he enlisted the help of one of his students there, Jennifer Balakrishnan. So we're going to start out today by considering a very classical problem, namely sums of two rational cubes. And as a result of looking at that problem, we're going to try to solve it using various methods. The first method that we'll try is using Heegner points, as they were described by Henri this morning and also yesterday. That unfortunately won't work, and so we'll modify our approach a little bit, and we'll look at something called mock Heegner points. After that, we'll look at a construction of Sachet, who uses these, and we'll reinterpret his result in terms of mock Heegner points and get some kind of solution to our diophantine problem. After that, we'll look at a theorem of Elke's. And then finally, we'll look at one more last application of these mock Heegner points to our problem. So that's general outline. So what we're going to do is we're going to be motivated by this problem, and then we're going to look at a variety of approaches to try to solve it. So let's look at this problem properly. So sums of two cubes. So the simple question is, which positive integers n can be written as the sum of two cubes of rational numbers? Okay, so that's something that you could describe to just about anybody on the street if they stopped you. So there's a famous example, which is not particularly relevant for my example, but 1729 is one such, and you can write it in two distinct ways as using integers. Here's another example. So if you consider the integer 94, 94 is also the sum of two rational cubes, and you would have to look pretty hard to find those rational numbers if you were just searching for them naively, and it's a little surprising. You won't be able to find any smaller solution. So that's the smallest way that you could write 94 as the sum of two rational cubes. The denominators are the same? Yes, they are the same. Are they not the same? 3605. I just copied them out of a program. Yes, they really are the same. Yeah. So if you consider as a projective point, yeah. So if they weren't the same, there would have just been some cancellation in the numerator and denominator. So anyway, okay. All right, so let's get started. So we're all good arithmetic geometers here. So for n, the positive integer, we define the curve E sub n, which is x cubed plus y cubed equals nz cubed. So that's a projective equation for the curve E sub n. And an equivalent question is which curves En have a non-trivial rational point. So there's a trivial point where z is equal to 0, and x is 1 and y is minus 1, or vice versa, which define the same projective point. So we want to know when is there a non-trivial rational point, so one with z not equal to 0. So if we take this obvious rational point, which I'll also call infinity, then you can see that the curve E sub n is given the structure of an elliptic curve. So it just comes to you as a genus 1 curve, and then you give it this rational point, and you have an elliptic curve, and therefore a group law, and you're happy because we like to study elliptic curves. And in case you're concerned about it, you can also transform the equation for E sub n into a Weierstrass equation. And this is now an affine equation, and there are different x's and y's, but there's a transformation that it comes to you in Weierstrass form like that. Okay, so already we should probably exclude the case where n is a cube or n is twice a cube, because we could always divide out by the cube. And as long as we make that assumption, then the torsion subgroup of En of q is just the point at infinity. So that means that an equivalent question to our original question is just which curves E sub n have rank greater than 0, so have infinitely many rational points. So if it has one, then it has infinitely many non-trivial ones. Okay, so this already we're going to restrict to the simplest case where n is a prime, at least 5. That seems like a good place to start if we're going to get anywhere. Okay, so as a conjecture, and you can find this conjecture in a paper of Selmer from 1951. It's very also attributed as far back as Sylvester in the 1880s, but I looked through all of his papers in that time, and I couldn't find any mention of it. But anyways, it's known today to be as Sylvester's conjecture. Anyways, it says that if p is a prime, which is 4, 7, or 8, mod 9, then P is the sum of two rational cubes. So you should burn in your head those congruence classes. P is 4, 7, or 8 mod 9. So that's what he conjectured. Okay, so where does this P4, 7, 8 mod 9, where does it really come from? Well, let's do a 3 descent on our curve E sub P. So we're looking for x cubed plus y cubed equals P. So if you do a 3 descent, then already for the congruence classes P is 2 or 5 mod 9, you get that 3 descent tells you the rank is less than or equal to 0. Okay, so therefore it is 0. It turns out that the 3 descent tells you that the rank is less than or equal to 1 if P is 4, 7, or 8 mod 9. And it tells you the rank is less than or equal to 2 if P is 1 mod 9. So the only prime we missed out on was, I guess, 3. But that's OK. All right, so like I just said, this immediately implies that the rank is equal to 0 when P is 2 or 5 mod 9. And in different language, but using an equivalent proof, this was proved by Sylvester in his 1880s paper, but also Lucan, Pépin. So that's a much older result. So what about this case when P is 4, 7, or 8 mod 9? Well, we know the rank is less than or equal to 1, so we should also look at the sign of the functional equation for the L series of EP. And it turns out that that sign is minus 1 if P is 4, 7, or 8 mod 9, and it's plus 1 otherwise. So that means that if you believe in the Burchard-Swinnerton-Dyer conjecture for P is 4, 7, or 8 mod 9, the Burchard-Swinnerton-Dyer conjecture says that the analytic rank should be odd, and we know that the analytic rank should be equal to the algebraic rank. We know the algebraic rank has to be less than or equal to 1, so we expect it to be equal to 1. So that's why the congruence class P is 4, 7, or 8 are distinguished in that way. So that's what we expect. So let's look at this case where P is 4, 7, or 8 mod 9. Okay, so we're going to assume that P is that way. So you can start looking at your favorite values of P and just checking to make sure if it's actually legitimately a sum of two cubes. So you can look at 7 and 13 and 17. I promised you numbers, so here's some of them. So 43. Okay, let's see how far. Okay, there are the dots. Okay, so you can keep doing this to your heart's content. You really can find all of the rational numbers just by a brute force search or your other favorite way to show that P is actually the sum of two rational cubes. Okay, so I just told you the BSD conjecture predicts that we should always have that P is the sum of two rational cubes, but we can't prove that. So we'd like to, in this very specific case, I mean, one option to prove the theorem, to prove Sylvester's conjecture, is to prove the BSD conjecture. In this case, that the algebraic rank equals 1 implies analytic rank 1, but you'd probably get a Fields medal for that, so we should probably aim a little bit lower and just do it for this particular class of curves. At least we know what to expect. Okay, so all of the things that Henri had mentioned today are including these special points that on x naught of n that correspond to elliptic curves with Cm. And so general philosophy, whatever that means, that predicts that when you have an elliptic curve that has expected rank 1, you should be able to prove that and explicitly construct rational non-torsion points on EP using this theory of complex multiplication, so using these special points on moduli spaces. So that's what general philosophy predicts. So let's see if we can put that to use. So the first instantiation of this notion of Cm points is Heegner points. So let me remind you what this means and introduce my notation. So the curve EP has conductor a capital N, and you can compute that it's either 9p squared or 27p squared, according as p is 7 mod 9 or 4 or 8 mod 9. So that's just a computation with Tate's algorithm. Okay, so that means that we have a modular parameterization x naught of n to EP. So it's going to be, we're going to have one whatever the conductor was. I just wanted to let you know what it was. Okay, and as we saw today from this modular parameterization, we can define Heegner points. So what's a Heegner point? Well, we take an imaginary quadratic field of negative discriminant d, which I'll call capital K. And what do I need to assume? Well, I need to assume the Heegner hypothesis. So here, the primes dividing the conductor are 3 and p. So I need to assume that 3 and p are both split in k. So in other language, what Henri said, so we say the pair EPK satisfies the Heegner hypothesis. All right, so here's some more notations. We're going to let OK denote the ring of integers of k. From the hypothesis, we know that there is an ideal in OK, which is a cyclic ideal of norm n. And that means, and as we saw the construction this morning, we obtain a cyclic n isogeny C mod OK, which is an elliptic curve with Cm by OK to this C mod the inverse of the fractional ideal. So this gives a CM point. We saw this morning that the CM point will be defined over the Hilbert class field K. So I'll call that CM point P. So the next thing we do, that's not too much help. So we have this point over on x naught of h. So the first thing we do is we use our modular parameterization to map it over to EP. And that gives us a point on E of h. And then we take the trace of that point from h down to k. And that gives us a point on EP of k. And that's known as a Heegner point. Okay, in this particular case, so we can add a torsion point if necessary and assume that this point y is an EP of q. So you can check that over k, the torsion points on EP is just equal to this little bit of the 3 torsion defined over k, so it's a z mod 3z. Okay, so this point y, we don't know anything about it. We get a point defined over q, but the real question is whether or not this point is torsion or not. So let's check it out. So when can we expect this point to be non-torsion? Well, as Henri explained, we have a Grossaugier formula which specifies when a Heegner point is 0 or not. So just to review, associated to the imaginary quadratic field K, which satisfies the Heegner hypothesis, we obtain this Heegner point y in EP of q. All right, so when is that point torsion or not? Well, we can check the Grossaugier formula, and they'll tell us. So what's the Grossaugier formula? It says that the canonical height of y is equal to the derivative of the L function associated to EP over k, evaluated at 1. And from the product expansion, this is, that Henri said this morning, this is an equivalent statement. Just the L series divides up as that. The little dot equals, I think he said equals star, so that just means it's equality up to a non-zero fudge factor. The important part is that it's non-zero, and if you really cared what it is, it's as periods and things like that. It can be made explicit. But the important thing is we want to know when the point is non-torsion, which is equivalent to knowing when the height of the point is not equal to 0. So it's enough to know, since this fudge factor is non-zero, just that the L series themselves don't vanish. Okay, so what do we need to do? Well, we need to choose a k such that this second factor, LEP over q, doesn't vanish. Because then it would say that the height of y vanishes if and only if this derivative of the L series vanishes. So equivalently, we should try to find this EP over a quadratic twist that has analytic rank 0. And if you assume the BSD conjecture, then you would have that the height of y is non-zero because we expect that this L prime will not vanish because we expect this elliptic curve to have rank 1. And so this construction really should give us a non-torsion point. So our point y will be non-torsion. Okay, so all of this says we expect a point constructed in this way to be non-torsion, but we have no proof. So we haven't really made any progress. We don't want to assume any conjectures, because if we do, then, I mean, we're just done. So, all right, maybe there's a way to use this to your advantage. So if you work algebraically, forget about L series now. So you have an algebraic construction of a point which you expect to be non-torsion on an elliptic curve. Maybe some way you can show that that point is non-torsion without saying anything about L functions. So that's certainly an option that you have. I happen to think this strategy seems really hard because you have to somehow pick your field K in a way that's natural, and I don't see a way to do that. Yes? That's over Q. Over Q, the torsion is trivial, and over K? I'm sorry? Oh, yes, the torsion is trivial, but it's possible that there's a non-torsion point. And so either the point is torsion or not torsion, and we want to show that it's not torsion.
So what cannot be torsion because it's defined on Q and we haven't any torsion point on Q?
It might be infinity.
Yes.
It might be infinity. Okay, yeah, so I'm sorry, you're right. There is no torsion except the origin. So, right, if it's either the origin, okay, I'm calling it torsion. It's either the origin or a non-torsion point. Yeah, thanks for that. Okay, I don't think that this is the most natural approach to try to find a point on x cubed plus y cubed equals p, but it's definitely an approach, and it shows already that Heegner points are a way. So in a specific example, if there were an emergency situation and you needed to know that p was the sum of two cubes, this would be an approach that you could take. So you could find your k and then you could compute all of these things explicitly, and then you would have your rational point. You would expect it to be non-torsion, and that would be fine. But we would like to be able to do this sort of more generally and in the most natural way. Okay, so the most natural way is to replace Heegner points with what's called mock Heegner points. So this is a variation of the above method, and they were called mock Heegner points, I believe, first by Monsky. But arguably, if you look at Heegner's original construction, I think he was constructing mock Heegner points, not real, what we call real Heegner points. But maybe that's not important. So don't be intimidated by the word mock. It's just not my fault. Okay, so so we always start out by picking an imaginary quadratic field. And here I'm going to pick the worst possible field, which is K, where you would join the square root of minus 3, or you would join omega, where omega is a primitive cube root of unity. Why do I say that that's the worst possible field? Well, it's because the number 3 appears absolutely everywhere in the constructions of all these things. So first of all, you notice that the elliptic curve En itself has Cm by OK. So you can see that in this model just by multiplying omega multiplies the x and y coordinates by omega. So that's definitely gives you an action. And here, okay, so the prime 3 is ramified in K. So that means the Heegner hypothesis is not satisfied. Okay, so 3 is not split in K. It's ramified. Okay, so that means we do not have a Gros-Sagier theorem, at least as it's been stated so far. Okay, but nevertheless, we have general philosophy at our feet. And so we can hope that Heegner-like constructions may still produce a non-torsion point, because that's what general philosophy says. So we failed with our Heegner points, but we might succeed by taking this particular imaginary quadratic field K. Okay, so let's see how we can use this field to our advantage. So I have to talk a little bit about twisting. Okay, so here's a really simple fact. So if we wanted to find a point on, let's say, r cubed plus s cubed equals p, well, of course, we could divide through the equation by p, and absorb that into the r and s by a cube root. And so, okay, that's just a fact. Okay, so let's consider this field L, which is you obtain by adjoining the cube root of p to k. So remember, k has a cube root of unity in it, so this is a nice Galois extension. All right, so here's an idea. So if we wanted to find points on EP of k or EP of q, what we can do is identify this EP. Another way of saying this is that it's the cubic twist of this curve E1, x cubed plus y cubed equals 1, by the cube root of p. All right, so then we can look for points on E1 of L that have this special form, namely the x and y coordinates are rational numbers divided by the cube root of p. Okay, so to be much more precise, so let sigma in the Galois group of L over k just multiply the cube root of p by omega. Okay, so the Galois group of k over q is generated by complex conjugation, which I'm going to denote bar. So what this means is what I've written down up above says that the group EP of q is exactly the same as the set of points r over cube root of p, s over cube root of p. And we can phrase that in terms of the action of the Galois group by saying we want to look at points y in E1 of L such that when you multiply, when you act by sigma, well, what will that do to the cube root of p? It'll multiply it by cube root. Since that's in the denominator, it's really like multiplying by omega squared. And we also want it to be fixed by complex conjugation. Okay, so that's just a restatement of that. So in other words, we're really looking for points on E1 with a specified behavior under the Galois group of L over Q. Okay, so let me do this more generally. Since this is a summer school, you might as well hear it in this generality. We'll use it later. So if E over Q is any elliptic curve with J invariant J, then there's a bijection between the set of twists of E. That means the set of elliptic curves with J invariant J up to isomorphism over Q, and this Galois cohomology set. So you take H1 of Galois Q bar over Q, and you look at the automorphisms of E defined over Q bar, and this is another way of denoting that set. Okay, so for us, remember, we have this EP of Q just as the set of points defined over L with special Galois behavior. So another way of rephrasing it is that we want the points y in E1 of L to satisfy this relation y tau is equal to this c tau of y, where c tau of y is this Galois cohomology class, this cocycle, which is just defined by this extension L over K. Okay? Alrighty, so that's the goal. So we have this new idea for a way to find a point on x cubed plus y cubed equals p. We'll look at x cubed plus y cubed equals 1, and we'll look at its cubic twist and try to find a point over this extension with nice Galois properties. Okay, so how are we going to do this? How are we going to find a point y? Well, first of all, we could take any point q in E1 of L and take a twisted trace of the point. So instead of just adding up all of its conjugates, which would give us a point down in k, we can add a factor, omega and omega squared respectively, on the Galois conjugates. That will also still be a point to find on E1 of L, but you can just check that q prime, when you act on it by sigma, you have this desired property that when you act on it by sigma, you do get the multiplication by omega squared. And in case you're concerned about this, to get down to q from k, one thing you could do is just take the trace. If you took the trace and you got 0, well, that means that q prime bar is the same as minus q prime, and then there's a way to fix that just by multiplying by the square root of minus 3, if it turns out that that's equal to 0. So you can really fix up the point. Once you have a point to find over k, you're golden. That's enough to get one to find over q. Okay, so starting with any point defined on E1 of L, we can take a twisted trace, and then we'll get a point on EP of q. All right, well, we still haven't done anything. We want to prove it's non-torsion. We still might get 0 after all this effort, but at least philosophy says that we should be able to succeed somehow. Okay, so let's give it a go. So we're going to try the simplest case where we can try to find one of these Mach Heegner points. Okay, so let me summarize it one more time. So if we can construct a point q on E1 of L, where L is obtained by joining the cube root of p, then by taking a twisted trace, we can construct a hopefully non-torsion point on EP of q. All right, so we're going to look to CM theory again to construct the point q. All right, well, here, remember, we don't have to worry about p because we twisted it away. So we're now looking at this constant modular parameterization, which is going to be fixed for this slide. It's just phi goes from x naught of 27 to E1. So here I'm saying that this x cubed plus y cubed equals e cubed, the Fermat cubic, just has conductor 27. So it turns out that x naught of 27 is a curve of genus 1. It's isomorphic to this E1. So that's nice. We don't have to worry so much about taking traces and things. All right, so what about this field L? Well, I said it was a nice Galois extension. In fact, it's obviously also an abelian extension, and you can compute the conductor of this extension just explicitly. So sometimes it's denoted by this frac L over K. I'm just going to note it by the integer f. And it turns out that if p is 4, 7 mod 9, then it's equal to 3p, and otherwise it's just equal to p if p is 8 mod 9. Remember, those are the three the congruence classes that we're interested in. All right, so what does that mean? So by computing the conductor, what I've told you is that L is contained in the ring class field H sub f of K of conductor F. So we saw an edelic description of that group today. You also, I guess, you have to know the Galois group is dihedral, but anyway, that's okay. All right, so where does this ring class field come from? Well, so we define this order, OK sub f, as just being the integers plus f times OK. So that's the order of conductor F. So how do we get a point that's going to be defined over this ring class field? Well, we consider a point P. So we want it to live on x naught of 27, so we need to find a cyclic 27 isogeny. And it needs to be between elliptic curves that have CM not by OK, which would just give us a point to find over the Hilbert class field, but rather with CM by OK, comma, F. So that's, if we can write one of those down, then we can map it by phi and do our twisted trace trick. So that's what we do. We define this Q to be the trace from the ring class field down to L under the modular parameterization. And then we can take the twisted trace. So, all right, so is the point non-torsion or not? That's sort of the end game here. All right, so let's literally see if we get a torsion point or not. So it's time to do an example. All right, so the smallest prime that we can consider is P is 7. All right, so I'm going to just, for this slide, and I'll probably use this later, for shorthand, we'll denote the elliptic curve C modulo the lattice generated by 1 and Z, just by this bracket Z. Okay, so here I've written down for you a cyclic 27 isogeny of conductor 3p. So it turns out that the middle bit, omega p to omega p plus 2 over 3, only has conductor p, and it's only the two curves on the outside that have CM by OK, comma, 3p. So that's the sort of thing you need to check. So how do you know that that actually has conductor 3p? Well, you're looking at the minimal polynomial, say, of omega p over 3. What's its discriminant? What field does it generate? That's all you have to do to check that. OK, once you have an isogeny, there's a way to normalize that by giving you a point in the upper half plane. So what do we get? So I've now written down this isogeny, and I'm taking p is equal to 7, so I should be able to tell you what this point is. We should compute it just with our bare hands. So here, since p is only 7, you can check that the ring class field is just obtained by joining a sixth root of minus 7. So in order to do computations, I'm really going to embed that into the complex numbers just by taking the usual primitive sixth root of unity and the sixth root of 7, the real number. All right, so now what do you need to be able to do? Well, I have this point z in the upper half plane. I need to be able to compute the modular parameterization just as a complex number. So I'll get these x and y coordinates, and there'll be some huge complex numbers. In this case, the phi map is an isomorphism, so I don't have to worry about that. So we get these complex numbers, and then you can try to recognize it over this field, which you really do know is the ring class extension. So you can. And actually, as you see, it's really not too bad. So it's just, well, what's written there. And so then you compute it to some more precision, and it really does agree with this. Another way to do it would be to compute not only the point, but also its Galois conjugates, and then look at its minimal polynomial, which is actually how I did it. But either way works once you know what the field is. And then afterwards, after you've recognized it, you can just check algebraically that these points really do satisfy x cubed plus y cubed equals 1. OK, so now we have this point defined over the ring class extension. So we trace it down to L, and if you hold your breath, it turns out to be torsion, which is very sad. So we tried really hard, and we still failed. So all right, it's torsion. You really do get 0 to lots of digits of precision, and that's just very sad. OK. So we failed. So you try other things. You try other p's. You should also try some other distinguished cyclic 27 isogenies. And they all just absolutely give you torsion. And you actually prove that these points always give you torsion on x naught of 27, if you want to. OK. OK, so in our first attempt at constructing a mock Heegner point using this modular parameterization, which was the first thing that we thought of, we only got a torsion point, which is a major bummer. OK, so now I'm going to show you a construction that really does work to try to motivate like why we should study mock Heegner points in the first place. So it does work, but it has very little to do with Sylvester's conjecture, unfortunately. But here's the statement anyways. This was proven by Sache in 1987. He says that if p is 2 mod 9, and instead of looking at x cubed plus y cubed equals p, we look at x cubed plus y cubed equals 2p, then you can prove, for real, that there are infinitely many rational points, that there's a non-trivial solution. And there's a little cousin to this result where you consider p is 5 mod 9, and you look at 2p squared instead of just 2p. So that's not the full-on Sylvester's conjecture, but it's still a theorem, and it's kind of a nice theorem, I guess. So what I'd like to do now is to give an expository treatment of Sache's theorem, just in the first case where p is 2 mod 9. And if you're really into this kind of stuff, I guess you can have an exercise of trying to prove it also for p is 5 mod 9. You really do get to get your hands dirty, and you just have to adapt the techniques that I'm going to show you today, changing p as appropriate. OK, so I just want to mention that Sache's original proof is housed in the language of modular forms. And here, so the only thing that I'm adding here is by rephrasing it in terms of the constructions that we've been doing using Heegner points and mock Heegner points. And from my perspective, it seems more natural and more comprehensible that way. OK, so what's the twisting here? So you always have to start with some kind of parameterization. So instead of considering x naught of 27 goes to E1, we're going to use some other different parameterization. So we're going to look at x naught of 36. So this is another nice modular curve, and it happens to have genus 1. It's an elliptic curve. And you can compute that this equation is just, I guess it doesn't get any simpler than this. Y squared is x cubed plus 1. OK? Well, why bother looking at that? Well, first of all, let me just identify these two curves using phi. All right, so somehow we want to get back to one of our curves, E sub n. So if you look at this curve over k, and you consider the cubic twist of E by the cube root of p, you can show over k that this is isomorphic to E of 2p. Okay, so if you want to do this over Q, it's actually the sextic twist of E by this sixth root of minus 27p squared. So, so that's what the sextic twist of E is. So y squared is x cubed minus 27p squared. And you can show that this is isomorphic to E2p just by computing the minimal Weierstrass equation. And this extra minus 27 just comes from the fact that we're also taking a quadratic twist by root minus 3, but that's an isomorphism defined over K. So we don't have to worry about it. So either way you want to think about it. It's really just a cubic twist, but if you'd like to work over the ground field and do it in terms of the cohomology classes, then you have to think about it a little bit more. Okay, so really explicitly what I've just said to you is that if you want to find points on E2p of Q, well, that's the same thing as finding points on E, so y squared equals x cubed plus 1, where they have this very special form. So I want the x coordinate to be something, a rational number, times the cube root of p, and I want the y coordinate to be a rational number times the square root of minus 3. That's what I mean by doing this quadratic and then a cubic twist. Okay, so in the same way, we have a Galois cohomology class, just as before. So this C tau is the cocycle where you consider tau goes to tau beta over beta. And here, so before we had the cube root of p, and here we have this sextic twist instead. Okay, great. So remember how this construction goes. So what we want to do is we want to find a point over some ring class extension, and then we're going to consider a trace, and then a twisted trace, and so on. So we better get started. So first of all, we were thinking about the elliptic curve x naught of 36. So I need to write down a nice cyclic 36 isogeny. So here it is. Just omega p over 6 goes to 6 omega p. The multiplication by 36. And you can compute that that has conductor 6p. And remember, our field L is already contained in conductor h of 3p. So we know that it will certainly also be contained in h of 6p. So that gives us this point p, using the identification phi, on E of h of 6p. So remember, E is just this curve y squared equals x cubed plus 1. Okay, so let me write down this diagram of fields. So we're starting up all the way at h. Yeah? What does that mean? That means that the elliptic curve, the smallest conductor for the elliptic, well, okay. So you look at the CM field, or well, really the CM order for each of these curves. So defined by C modulo 1 comma omega p over 6. So so that has an endomorphism ring. That endomorphism ring, I'm claiming, is the order of conductor 6p in OK. And similarly for the target, yeah. So if your source, so you have to take the LCM of those, because that tells you where the full isogeny is defined over. So that's all I mean by that. Thanks. Any other questions before I get back to tracing? Okay. So we have this point, omega p over 6, to 6 omega p, and it defines a point on the field h of 6p. So we have a long way to go to get from h of 6p all the way down to k, and then therefore to q. So I've written the degrees of these extensions there. So one thing you could do is to just take a trace down to L, like we were saying. But it turns out that if you're very savvy, the trace from h of 6p to h3p is needless in the following sense, that if you take this row in the Galois group of h6p over h3p, it turns out that this is, well, it's just given by the cube root of 2. So that splits off as a direct factor in this Galois group. So you can define it as an element of h6p over k, and it's just x on the cube root of 2 in the usual way. So you can actually prove that if you take this original point p and you act on it by rho, it satisfies this equation. P rho is equal to p plus 0, 1. So 0, 1 is really a point on E, as you can see, and it's a 3 torsion point. Okay? So what does that mean? If we were just doing this in a simple-minded way and took the trace, well, we take p plus p rho squared. And what is that, after all? Well, it'll be 3p times 3 times this torsion point. Okay, so we don't really need to multiply our point by 3, which is what we would get if we took the trace. So instead, we're going to be really slick, and you can look at some other torsion point on E, which is defined just over h of 6, which is just k adjoin the cube root of 2. And it also satisfies this functional equation, T sigma equals T plus 0, 1. So if you put these together and you consider instead P minus T, and you look at how the Galois group acts, well, it'll act on P by adding 0, 1, and then it'll act on T by subtracting 0, 1. So that means that P sub T is fixed by rho, and that means it automatically descends from H6P to H3P. Okay, so maybe you weren't bothered by multiplying this point by 3, but as you know on elliptic curves, whenever you multiply a point by 3, you really cause the height to get a lot bigger. So it's 9 times the logarithmic height. So if we really wanted to compute with these things, we don't want the digits to get very big. And also, we're going to have to do this trick later in some other examples. So this is a way of saying, well, let's really look at how the Galois group acts before we go nuts and taking traces. Okay, there's my field diagram again. So we started with the point P on H of 6P. I'm sorry, it says 9P. So that by subtracting this torsion point, we're able to descend it to H3P. All right, so now let's go nuts and take the trace down to L of this point. So that gives me a point on E of L. Okay, so we have to prove something about this point Q. So I'm claim that if in a similar way we can look at how the Galois group acts. So how does the Galois group? So sigma is this element which takes the cube root of P to omega cube root of P. And I claim that if you take the point Q and act on it by sigma, you get a similar looking equation. You multiply Q by omega and you add a different 3 torsion point. Actually, I think, yeah. That's also a 3 torsion point. It's just the negative of the other one. Okay. So I'm going to call this key equation sigma. So from this equation, it's pretty easy to see. Remember how the twisted tracing works. Instead of just summing all of the conjugates, we add a factor of omega or omega squared, depending on which conjugate we take. Well, if you use the key equation, it's easy to see that the twisted trace is just actually multiplication by 3. And so this point y really gives you a point on E2P of k, just because it's the twisted trace. Okay, again, if you want to worry about getting down to Q, you can show that Q bar also satisfies one of these nice equations. So in fact, already this point y is defined over Q. All right, so bugger, the thing that's always leering in the background is easy to construct points on elliptic curves, but the hard part is to show that it's non-torsion. So here, because we have a key equation at our disposal, we're going to be able to show that this point y is non-torsion. So y is just 3 times q. So if we want to know that y is non-torsion, it's enough to know that q is non-torsion. Okay, well, let's suppose that q was torsion. Well, q is defined over L. So what is the L torsion on E? Well, it's just these 3 torsion points, 0 and 0, plus or minus 1. That also happens to be already all of those points are defined over Q. All right, so now we have to check if each of these points S satisfies the equation sigma, which we know that Q satisfies. Okay, well, S sub sigma is just S again. And also, multiplication by omega just multiplies the x coordinate by omega. So that's also fixed by multiplication by omega. Okay, so if you plug that back into the key equation, you get S equals S plus 0, minus 1, and that's a contradiction. Okay, does that make sense? So using just this key equation, you can, and the action of the Galois group, you can really convince yourself that the point is non-torsion. Okay, so let me give you an indication where this magic key equation really comes from. Okay, so I'm going to do something a little bit more. I'm going to prove the equation for P. So remember, I started with the point P, I subtracted a torsion point, and then I was able to descend that to this point P sub T, and then I took a trace down to Q. So I'm actually going to be able to say how the Galois group acts up here, and that will, it's not hard to show that implies the equation sigma just by taking appropriate traces. You have an abelian group acting, so it's not hard to show. So to prove the equation sigma, we're going to use 2 key ingredients. So the first one is an explicit calculation with the Arden Reciprocity Law, which tells you how the Galois group acts. And then the second one is we'll use an explicit identification of this action with what's known as a modular automorphism. So what does this really mean? What's a modular automorphism? Well, okay, this is a little funny. So we're going to find a matrix which normalizes gamma 0 of 36 such that when I take my point P and I act on it by M, I get the same thing as if I applied sigma to the point. So that may seem a little bit weird. I mean, you know how the Galois group acts on a set of points of a curve. It acts just discontinuously. It's absolutely bizarre. And here I'm going to take this particular point P, and I have its image, P sigma. Well, I'm just going to look for an automorphism which maps one to the other, and then hopefully I'll be able to figure out what this automorphism is, sort of acting on the full curve, and that should tell me what sigma really does. So we're going to identify M. Since it normalizes gamma 0 of 36, it's an element of the automorphism group, and then that will tell us what the relation is. Okay, so we have two ingredients. The first one is the Modular reciprocity law. So first of all, I have to choose a lift of this sigma, which a priori is just acting on the cube root of P all the way up to H of 3P. So here's how this works. So we identify the Galois group using the Arden Reciprocity Law. So we have to give you an ideal class. So let's let this alpha sub sigma just be 1 plus 2P omega. Okay, that's just some element of OK. So the way that Arden reciprocity works is we consider the ideal, which is this generated by alpha, and then we consider it as an invertible ideal in OK, comma 6P. You just intersect it. So Arden reciprocity says that there's an isomorphism between the class group of OK, 6P and the Galois group. And if you look at that map, that means that this ideal I sigma, you can show directly by a computation that this element sigma acts on the cube root of P like you want it to. So you have to really be able to get your hands dirty to see what the Arden law works on. So remember, this P is given by an isogeny omega P over 6 goes to 6 omega P. So the Modular reciprocity law acts as follows. Well, you just multiply this lattice 1 comma omega P over 6 by the inverse of the ideal I sigma. You do that to the source and the target, and that gives you a new isogeny of conductor 36P. Or, yeah, a new cyclic 36 isogeny. Okay, so in order to figure out what P sigma is, we need to multiply out what this I sigma inverse is times omega P over 6. Okay, so I sigma inverse is just alpha bar intersecting. And what you need to do now is, so you have literally, you have two ideals in an order, and you want to multiply them out and see up to homothety what it's generated by. Okay, so you can multiply that out, and you get this element 3 omega P over 2, and up to homothety, because that gives you an isomorphic curve, and therefore an isomorphic isogeny. And if you do the same thing to the target, you get this other element, 2 omega P plus 1 over 3. And so what we've proven now is that P sigma is it's going to be some other 36 isogeny. It's some other point on x naught of 36, and it's just given by this one instead. Okay, so that was step number 1. So now we have to find, so just to remind you, we're trying to prove this equation that tells me how sigma acts on P. All we've done so far is that I've computed what P sigma is just as an isogeny. So now what I need to do is to find a matrix, like I claimed, such that at least how it acts on P is by the image of this other isogeny. Okay, so if you go hunting around for automorphisms, well, the two ones that you immediately find are the Atkin-Lehner involutions, W4 and W9. And you can write down explicit matrices for those. They have the modular interpretation. And it turns out in this specific example, there's also what's known as an exotic automorphism. So this really harmless-looking matrix 1061 is an element of order 6, and it also normalizes gamma 0 of 36. So these were first studied by Ogg. So you go back to those papers. So if you consider the group H, which is generated by these three elements, you turn out to have a solvable non-commutative group of order 72. So that gives us lots of possible M's that we can try to see which one gives us P sigma. So maybe you run a computer first to try to find it, and then you prove it to yourself that this actually works for all values of P, and you can check this directly. Okay, so this point M corresponds. So now we have our candidate M. So M is now just an element of the automorphism group of x naught of 36. And here I'm considering it as just a genus 1 curve. So when you consider automorphisms of elliptic curves, they have to fix the origin. But here I'm just considering it as an abstract curve. Okay, and as an abstract curve, we know, well, it's still genus 1. So we know that any such automorphism is given by multiplication by mu6 plus the addition of some torsion point. And this will hold for all points z in x naught of 36. So how can we figure out what M of z actually is? Well, we have to determine what the A and the B are. And so we can do that by looking at how it acts on the cusps of x naught of 36. So we're left to do just one more computation. So we have the point infinity on x naught of 36. And under our choice of a modular parameterization, it turns out to be the origin of the elliptic curve. All right, so you can plug in infinity into this matrix M. And if you do that, well, it would be 9 times infinity minus 4 over 36 times infinity minus 15, which is 1/4. OK, so what's 1/4? That's another cusp. And so you can see its image under the modular parameterization, and it's this torsion point minus 1 comma 0. So that means that b is equal to minus 1, 0. And in a similar way, if you evaluate at the cusp 0, you find that a is equal to omega. OK, so that means that we have now proven that m, let me go back. So we've proven that p sigma is the same thing as m of p, and we know how m acts. And so that proves our equation for p. And then if you take the trace, you get that key equation sigma. And then that was what enabled us to show that the point was really non-torsion. OK, so that was, and that all just came from computations with our bare hands. OK, time for another example, I think. OK, so let's really see how this works in practice. OK, so I have to take a prime which is 2 mod 9 in Sauché's construction. So the smallest such is p is equal to 11. All right, so remember we have this cyclic 36 isogeny, which is just omega p over 6 goes to 6 omega p. And you can compute this point p under the modular parameterization and all of, let's say, all of its Galois conjugates. And so you find its x-coordinate, and it satisfies some huge equation. OK, I guess there's not an equals 0 there, but that's what I mean. I mean that this is the minimal polynomial for x. OK, well, I fit it on a slide. I'm not telling you what the y-coordinate is, but you can also compute it. All right, so you remember how this works. It's tricky. We don't just take a trace now. Remember, we subtract off this crazy torsion point. So let's do that. So it's this torsion point minus the cube root of 4, comma, minus the square root of minus 3. And now that's supposed to be a point which is defined over h of 3p. OK, so now let's look at that point pt, and its x-coordinate is now much nicer, so I can increase the font size. And so that's the polynomial that now the x-coordinate satisfies. And you can see it really did descend to a degree 3 extension. So it was good that we didn't just take the trace, because then the coefficients would have blown up. So we worked really hard to get a small equation like that, if you consider that to be small. OK, so now we have to take the trace from h3p over L of this point plus a torsion point, and that will be a point defined over L. Unfortunately, again, all of these are just up to the precision that I can calculate them as complex numbers. I haven't proven that these are actually the points. But you can pretty well convince yourself that this is really the point that it is by taking enough precision and not getting anything new. OK, so that really is a point, like I said, defined over L. So the only things that appear are omega and the cube root of 11. All right, so now you can check. If you take sigma and you take the cube root of 11 to omega cube root of 11, you can just check if you subtract off omega times q, just algebraically, that it does satisfy our key equation. OK, so now, and lastly, we take the twisted trace, which is the same thing as multiplying our point q by 3. And we end up with this other point. And so so that cube root of 11 is really good. That's what enables us to pull the factor 11 in. And remember, this is of the form that I wanted it to be. I wanted a rational number times the cube root of 11. The omega doesn't really matter. That's what I mean by the descent decay. And also the y-coordinate is something times the square root of minus 3. And so there we go. All this work, and I've successfully constructed rational numbers x and y so that x cubed plus y cubed equals 2 times p, which is 22. OK, it turns out that this is twice a Mordell generator, so maybe a slicker approach would have given us a smaller coordinate, but maybe not. Maybe the 2 has some kind of significance, and we'll always get it there. But the nice thing about that is that all of these computations are really fast. They all just require analytic computations to a certain precision, and so this takes a couple of seconds to produce these rational numbers. So it's really very much more effective than searching for them, because the denominators and the numerators will get quite big. OK, great. So all that, I hope that you found those rational numbers to be pleasing. I don't mean to get back to the original problem, but that has absolutely nothing to do with Sylvester's conjecture. So we started out by wanting to know that P was the sum of two rational cubes, and, well, we considered a different problem. Okay, well, we solved that one, but let's get back to Sylvester's conjecture. So let's get back to what we were trying to prove. I mean, that's not a bad idea in mathematics sometimes, just solve a different problem that you can solve. But anyways, so already 12 years ago, Elke announced the following result at ANTS 3. He said that he could prove Sylvester's conjecture if P is 4 or 7 mod 9. So he could prove that x cubed plus y cubed equals P and also equals P squared. They both have infinitely many points. So he's gone now. This has never been published. So, and it's been 12 years. Salmon and I sat him down at Harvard one time and made him explain it to us. And he sketched some of the details, so I can tell you a little bit. So you have to write P as pi times pi bar, where both of these are elements of K, where they're normalized to be 1 mod 3. So he does something funny. He defines a modular curve defined over K, which is, again, adjoin the cube root of unity. And here he uses some sort of pi level structure. And from this, he gets a modular parameterization to e of pi. So you get some x cubed plus y cubed equals pi. And that's defined over K. And then he uses this map phi to define a point on e of pi, which is defined over the cubic twist by pi bar. Okay, so that twist to give you a point on EP of K. Okay, that's all I can tell you about how his method works, really. So it's a little bit, it's quite interesting. All right, so what I can tell you is that there's a different way to go. If you just want to stick to our tried and true method of using mock Heegner points, you can prove the following theorem. If P is 4 or 7 mod 9, and 3 is not a cube modulo P, so asymptotically that includes 2/3 of the primes P, so that's not too bad. Only 1/3 left to go. We can prove that P and P squared are both the sum of two rational cubes. Okay, so let me tell you, so we're revisiting mock Heegner points. So now that I've set up all these detailed constructions, let me tell you just a little bit about how our construction works. So the first part, we have to start out with some fixed modular parameterization. We've already seen ones coming from x naught of 27 and x naught of 36. So here we're going to go a little crazy and consider the parameterization x naught of 243. And this has a map to the elliptic curve E9. So that's x cubed plus y cubed equals 9. Be very afraid. So x naught of 243, so 243 is 3 to the 5th. And this curve has genus 19. Okay, so this is definitely not an isomorphism anymore. Wow. Okay, so you guys remember how this goes. So you have to start out with a cyclic isogeny of a good enough conductor so that you know that the cube root of P embeds in this conductor. So here we have to go all the way up to 9P. So that gives us a point on E9 defined over H of 9P. So we're slick. And just like with our original mock Heegner point construction, subtracting off a torsion point, something analogous, you can take a twist, and already you get a point. So it's not defined on x cubed plus y cubed equals 9 anymore. It's defined on x cubed plus y cubed equals 1. And it descends from h of 9p to h of 3p. Okay, so once you have it there, you trace it down to L. And you prove a key equation. So you show that the action of sigma, mapping the cube root of P to omega cube root of P, just acts by omega r plus t, where t is a 3 torsion point. Okay, so you take this point r, and in this particular example, you get a point on EP squared of k, or if you take a different isogeny, you get a point on EP of k, just by taking the twisted trace. And whether or not you get a point on EP squared or EP depends on this original choice of P. So we have lots of possibilities for the choice of an isogeny of 243, cyclic isogeny. So that gives us the difference between P and P squared. So we would be done, like before, if we could show that no torsion point satisfied this equation, S sigma equals omega S plus T. But it turns out there are torsion points. So we don't just get to conclude by just a contradiction. So we have to work a little bit harder. So to prove that R is non-torsion, we take the point R, and we look at it mod P on E9. And it turns out that this modular parameterization, you could give it explicitly by eta products. And as a result, when 3 is not a cube modulo p, you really do reduce it and you do a computation, and you can show that what you end up with is not the image of a global torsion point. So you have to work a little bit harder. I'm not going to say more details about that. Instead, let's do an example. So let's show you how this really works for p is equal to 7. So I failed with x naught of 27, but maybe I will succeed here. So first of all, I write down a cyclic 243 isogeny. And as conductor, 9 times 7 is 63. So I think we're used to this now. So first of all, we end up with a point P, which is defined on E9. And looky here, it's not too bad, actually. The x and y coordinates satisfy these very small equations, which is good. That means we're getting very close to a generator. Our coefficients aren't too big. So now we take a twist, like yeah? How do I write down the equations for x and y? So what I do is I can compute just x and y as complex numbers, but I can also use, so if I wanted to, that would almost be enough, because I could try to use LLL to recognize those complex numbers, find a small polynomial that they satisfy. But actually, I can use the Modular reciprocity law, like I showed you in the example, to actually compute all of the conjugates under the Galois group. And once I have that, I can just multiply them out, the minimal polynomial, and then just try to recognize the coefficients, which is easier. But either of those works. And yeah, OK, great. So I had this point on E9, and I twist it, and I end up on E1. So here, remember, we just have h of 21, so h of 3p it was obtained by joining the 6th root of minus 7. So you recognize the point. You take a trace down to L, and you end up with this point. And once you rewrite that in terms of the original equation, you end up with this point y. So that means at the end of the day, we end up with 11 over 3 cubed plus minus 2 over 3 cubed is 7 squared. So that's not too bad. And again, that runs really, really, really quick. I guess you could have found that one by searching. So maybe that's not so impressive. OK, let me conclude by saying, relating this back to the Gros-Saulgier formula. So remember, when we were just considering regular Heegner points, if we could find a quadratic twist with analytic rank 0, then the BSD conjecture applies that our Heegner point didn't vanish. So what really explains how sometimes the mock Heegner point vanishes and sometimes it doesn't? We should have a Gros-Saulgier formula for that. So if you believe some kind of Gros-Saulgier formula should hold, it would look like this. So the height of a CM point y is up to some factor, the derivative of, let's say, E9 over k, by now I'm considering not the quadratic twist, but the cubic twist. So that means I have to consider this cubic character associated to the field k adjoin the cube root of 3p. OK? So now, again, you have just a factorization of the L function into two factors. So you take the derivative, and you can, I guess, prove that one of the L functions, the one associated to EP, has to vanish to odd order. So you know that L itself vanishes. So that gets rid of one factor when you do the product rule. And you end up with this height of y is equal to this product of two L functions. OK, so the first factor is the thing that BSD says we expect it to be non-zero, therefore it's rank 1. And so if we want y to be non-torsion, then we want the height to be non-zero. So that means we want this L of E3p squared to be non-zero. Okay? So you can look at that. So when 3 is not a cube mod p, you can do a 3 descent and show actually that the rank is equal to 0. Okay? So that's why we expect this point y to be non-torsion in the construction that we give. Okay, so if you want to remember how Sautier's construction worked, here we considered a point on the cubic twist of E2 by the cube root of p. So here we have another height of y as the product of two L values. The first one is the one that we expect to have rank 1, so we expect it to be non-vanishing. And we have this other cubic twist factor. And again, you can prove that E of 2p squared, that actually, to do a 3 descent, it has rank 0. Okay, so in this game, what you want to do is you want to find a curve and cubic twist such that you can prove that the cubic twist actually has rank 0, and then you expect the CM construction of mock Heegner points to give you a non-torsion point. Okay, so big question. All right, so this was all heuristic, I guess. What is the statement of the Gros-Sagier formula in the cases when the Heegner hypothesis does not hold? So Gros-Sagier assumes that the conductor of the curve and the discriminant of the field are relatively prime, and they get a theorem. So here we really don't have that, but we still expect some kind of formula. And not only do we expect it, I mean, we really do have situations where it explains what's going on. So what is the statement? If you want to get a heads up on it, I think that would be a great theorem to prove. You have to beat Ben Howard to it. He's working on it right now, Boston College. Okay. So let me say just a little bit about P is 8 mod 9, because that's the case that I neglected. So I only looked at P is 4 7 mod 9. So we have a construction that it also uses x naught of 243 and a cyclic isogeny of conductor 9p. You add a torsion point. You descend with a twist. You end up with a twisted trace on EP of Q. And you want to know if it's non-torsion. So by the previous slide, here Gros-Sagier says we have the product of two derivative of an L value and this other L value. So in the previous cases, we could show the second factor really was non-vanishing, if you believe BSD, that they really just have algebraic rank 0. Okay, unfortunately here, for our construction for P is 8 mod 9, the reason I didn't include it in the theorem is because we can't prove that anymore. There's no simple criterion, at least that we can see, which controls when E of 9p squared has rank 0. We don't really know. It seems somehow to depend on P, not just on its congruence class. Okay, so here's a question for all of you. If you assume that this L value is non-zero, presumably the point Y should be non-torsion. And if you compute all of the examples, that's exactly what happens. So that's certainly something you could consider and that we're also trying to also prove. So you have this algebraic part of the L function, and you want to somehow use that, if you know that it's non-zero, to prove that your point's non-torsion, or at least when 3 doesn't divide it. Okay, so in conclusion, what we've seen is that Heegner points, which maybe start out in abstract theory and then you prove great theorems from them, actually, if you want to get down and dirty, they can be made very explicit, actually computing points. So, and actually, they're also very, very efficient. So even with large values of P, you can compute these X and Y. Once you've given up on Heegner points, or maybe you're like Heegner and you consider mock Heegner points to be the real Heegner points, you can consider their cousins as mock Heegner points. So those arise when the Heegner hypothesis is not satisfied. So that means the conductor of the elliptic curve and the CM field that you considered weren't relatively prime. And those mock Heegner points, we've seen a couple of examples now where they really solve very concrete problems in diophantine equations. So there's still several open questions, like prove a Gros-Sagier formula in this case, as well as other constructions. So if you want to take your favorite family of x cubed plus y cubed equals